So to get started in 15.3, we want to remind ourselves of some properties of one-dimensional derivatives. So for one-dimensional derivatives, we had a critical number, and a critical number was a zero of the first derivative. So a critical number was a number c such that f prime of c equal to 0. And if we remember, the derivative represents the slope. So if we were talking about a graph of something in one-dimensional calculus, anywhere we had a slope of 0, so somewhere like this, was a potential point to have a maximum value or a minimum value. Turns out, in business, we really like to maximize things and we really like to minimize things. So we need to be able to generalize from the one-dimensional version of setting the derivative equal to 0 and solving to find our critical numbers, so then we could find maxes and mins. We're going to generalize this process to what we're going to be talking about now with a multivariate function. So our first definition says the following, or our first theorem: if f has a local maximum or minimum at the point a comma b, and the first order derivatives of f exist there, then f sub x of ab equals 0, and f sub y of ab also equals 0. So this is that two-dimensional analog of what I was just talking about in one-dimensional calculus. So then AB is called a critical point or a stationary point of f. As in single variable calculus, not all critical points give rise to maximums or minimums. If f is continuous, this is a necessary but not sufficient condition for there to be a maximum or a minimum value at a point. All right. So let's go ahead and analyze this graph. So this graph is a little bit interesting in 3 dimensions, because if we were to look at a cross-section of this graph on the x-axis, so in the x direction, so if I set, say, y equal to 0, my cross-section would look something like this, and it's going to come back down. And so in that cross-section going this way, it would appear that my graph would have a maximum here, which would be this point sitting right about here. But if I took a cross-section of this graph now with respect to y, so a y cross-section, where x is equal to 0, my parabolic chunk would look something like this. And if I looked at that cross-section, what does my graph appear to have at this point? A min. So depending on which cross-section we look at, this graph has in one direction a max and in another direction a min. We couldn't have this situation in one-dimensional calculus. This point right here is given a special name where it's a maximum in one direction and a minimum in another. This is called a saddle point. And you may remember that word from one-dimensional calculus when the derivative was equal to 0, but you didn't get a max or a min. And you might have wondered why they called it a saddle, because it doesn't look like a saddle in one-variable calculus. But here, if you look at the shape of that graph, it's not a great saddle, but you could imagine sitting in that and going for a ride on a horse, right? Sitting in here, your legs would go down where the red parabola is, and your body would sit up in the front and the back where the green parabola is. So that's what gives rise to that name of a saddle point. And this goes back to the point that it is a necessary condition for it to be a max or a min, but it's not sufficient. So the possibilities that we can have then at a critical number is that it can be a max, it can be a min, or we could end up with a situation like this where it is neither a max or a min, it's a saddle point, and it maximizes in one direction and minimizes in another. All right, so let's take a look at our next example, which is going to give us another theorem, and then we will look at the example that goes with it. So in one-dimensional calculus, we had a method for finding maximum and minimum values, which was we would find the derivative, set it equal to 0, and find the critical points, and then use either the second derivative test or the first derivative test to determine if a point was a max or a min. Well, we have the second derivative test, which is the only one we're going to cover in this class, for a function of more than one variable. So it says, suppose AB is a critical point of the interior of the domain of the function f. So remember, a critical point is where the first derivatives are equal to 0. We then form the number h, which is equal to f sub xx at AB times f sub yy at AB minus the mixed partial squared. And that is going to give us a number h. Then, depending on the value of h and f sub xx, we will know what we get. So if h is a positive number, we are either going to have a local maximum or a minimum, and we get a local maximum or a local minimum if f sub xx is positive, and we get a local minimum if f sub xx is negative. If h is less than 0, then we get a saddle point, and if h equals 0, the test fails, and we would have to use some other way to determine if we had a maximum or minimum value. All right, so let's do an example of using the second derivative test. So find the local maximum and minimum values and saddle point of f of xy equals x squared plus 2y squared plus 4xy. So in order to use our second derivative test, we need to find our critical numbers is the first thing. So we need to find df dx So our df dx is going to be 2x, and then the derivative of 2y squared is 0, and then 4xy we are going to get plus 4y, because the derivative of our x is going to be 1. And then we take our next partial derivative, df dy, and that's going to be the derivative of x squared is 0. We're going to get 8y cubed plus the derivative of 4xy is going to be 4x. So then we need to find all points x and y where these two things are equal to 0. So we need to solve the following system of equations. So we have 2x plus 4y equals 0, and 8y cubed plus 4x is equal to 0. So we're going to need to do the substitution method. So I'm going to solve the first equation for x by minusing 4y and minusing 4y, and we get 2x equals negative 4y. We divide by 2, and we get x is equal to negative 2y. So we're then going to substitute this into the other equation. So that's going to give us 8y cubed plus 4 times negative 2y is equal to 0. So then I would get 8y cubed minus 8y is equal to 0. And we need to factor to solve this equation. So we factor out in our GCF, which is 8y, leaving us with y squared minus 1 is equal to 0. And then we factor y minus 1. Our difference of squares, y plus 1, is equal to 0. So we get three solutions. The first one gives us y equals 0. The second one gives us y equals 1. And the third one gives us y equals to negative 1. So then pairing those up with each of these, if we have x is equal to negative 2 times 0, we get 0. We have x is equal to negative 2 times 1 is negative 2. And x is equal to negative 2 times negative 1 gives us positive 2. So our ordered pairs are 0, 0. We have 1 and negative 2. And we have negative 1 and 2. And those would be our three ordered pairs for this, or for our three critical numbers for this graph. So now that's the first part. We've just found our critical numbers. Now we need to take some more partial derivatives so we can evaluate this value. It's called the Hessian Matrix, if you're wondering. That's why they call it H. But we're just going to evaluate H. You don't need to know the name. That's just a bonus fact. So to do this, we need f sub xx and f sub yy and f sub xy. So we have our partial derivatives. So let's keep taking our derivatives. So df d d2f dx squared is going to be 2, and d2f dx dy, so the mixed partial here, so if I take the derivative of this with respect to y, I'm going to get 4. And notice if I take the derivative of this one with respect to x, that would be 0, and the derivative of 4x is 4. We get the same thing for the mixed partials. And then d2f dy squared, we're going to get 8y cubed, so we take that down in front. 3 times 8 is 24, y squared. So we form H, and recall our H is f sub xx times f sub yy. So f sub xx is 2 times f sub yy, which is 24y squared, minus this thing squared, our mixed partial, so 4 squared. So h, we get 48y squared minus 16. And now we need to test each of our points. So h of our first critical number, h of 0, 0, is going to be 48 times 0 squared minus 16 equals negative 16. So then we have this critical number at 0, 0 is negative 16, and our d2f dx squared, or f sub xx, is 2. So if h is negative 16, that means we're here. Then it tells us that that is a saddle point. So 0, 0 is a saddle. Now we test our next critical number, which is 1, negative 2. So h of 1, negative 2 is equal to 48 times negative 2 squared minus 16. And it doesn't seem we can trust my arithmetic today, so let's use a calculator. 48 times negative 2 squared, take away 16, is going to be a positive number. So we have 176, and our second partial with respect to x is still positive 2. So this time we have h is positive, and our second derivative with respect to x is positive. So by 1, we're going to get a local minimum. And that's 3 above, if I remember correctly. Yep. And then our last point that we need to check is negative 1, positive 2. And we're going to get the same value out of this because negative 2 squared and positive 2 squared are the same thing. So we get 176. So once again, by 1, negative 1, 2 is a local min. So we then found our local max and our local mins. Well, actually, we only had local mins and a saddle point in this example. But that is pretty much our process for finding maximum and minimum values for that function. So it tells us for our function x squared plus 2y squared plus 4xy, we're going to have minimums at 1, negative 2, and at negative 1, 2. We need to find our partials. So let's go with f sub x is going to be 2xy minus 2x, and f sub y is going to be x squared minus 4y. And just because we're going to need them, let's take the rest of our partial derivatives. So f sub xx is going to be 2y minus 2. F sub xy is going to be 2x. And f sub yy is going to be negative 4. So now we need to solve for a critical number. So we have 2xy minus 2x is equal to 0, and x squared minus 4y is equal to 0. So there's a few different ways that you can resolve this problem. One is you could solve equation 2 for y and substitute into the other equation. The other thing we might notice is that equation 1 has a GCF of 2x in both things, so if I factor that out, I get 2x times y minus 1. Well, I can set each of those factors equal to 0, so 2x equals 0, divide by 2, I get one solution as x equals 0, or y minus 1 equals 0. So if I add 1, I add 1, that gives me y is equal to 1. So then I can actually just put those in to the other equation, and if I do that for x equals to 0, I get 0 squared minus 4y equals 0. So that's going to be negative 4y equals 0, divide by negative 4, divide by negative 4. So that gives me the solution y is 0. So one of my critical numbers is going to be 0, 0. I also have y equals 1. I can put that in, and that would give me x squared minus 4 times 1 equals 0, which is x squared minus 4 equals 0. That factors as the difference of squares into x minus 2 times x plus 2, which gives me x equals 2, or x equals to negative 2. And those both came from y equals 1, so that gives me two more critical numbers, 2, 1, and negative 2 and 1. So those would be our three critical numbers. So now we need to create our h. So we're going to have h is equal to, remember our formula for h is f sub xx times f sub yy. So our f sub xx was 2y minus 2. And our f sub yy is negative 4 minus f sub xy, which is 2x squared. So simplifying this up a bit, we get negative 8y plus 8 minus 4x squared, or negative 4x squared minus 8y plus 8. So then we plug all of our values in. So h of 0, 0 is equal to negative 4 times 0 squared minus 8 times 0 plus 8 gives us 8. So we go look at our chart again. And if h is positive, okay, so that puts us in these two cases. We're going to have either a local max or a local min. To find out if it's a max or a min, we have to evaluate f sub xx. So our f sub xx is 2y minus 2. So f sub xx evaluated at 0, 0 is going to be 2y minus 2. So 2 times 0 minus 2 gives us negative 2. So since this is negative by, I don't remember if it's 1 or 2 in our chart that we had up here, it's going to be a max. Because if it's negative, we then get a local maximum. So by 2, we get a local max. Now we need to calculate h of 2, 1. And h of 2, 1 is going to be negative 4 times 2 squared minus 8 times 1 plus 8. And here 2 squared is 4 times negative 4 is negative 16 minus 8 plus 8 gives us negative 16. So that's going to tell us that it is a saddle point. It's by 3. And then lastly, we try h of our last critical number, which is negative 2, 1. And it's going to be the same thing, because negative 2 squared is the same as positive 2 squared. So it's also going to be a saddle point.